Hello and welcome to the second session on nucleophilic substitution reactions. In the previously uploaded video, the link for which you can find here, we discussed different types of nucleophilic substitution reactions. In fact, we saw how many different types of nucleophilic substitution reactions could we have. Today, we are going to focus on the first of those nucleophilic substitution reactions, and it's a unimolecular nucleophilic substitution reaction, which we also know as the SN1 reactions. These reactions are known as unimolecular because of the fact that its rate determining step involves only one molecule. It's a nucleophilic reaction. Nucleophile is involved. It's a substitution reaction, so a nucleophile will replace a group in a molecule, but its rate determining step will involve only one molecule, and that is why these reactions are known as unimolecular reactions. And the whole mechanism takes two steps to complete, or the whole reaction is completed in two steps. This is a general reaction for a unimolecular nucleophilic substitution reaction, and you can see here we have an alkyl halide which will react with the nucleophile, and in the end we will have a bond formation between the nucleophile and the R group, and a halide anion will be released as a result. Let's see the general mechanism for this reaction. As we saw earlier, that this reaction completes in two steps. So the first step, which is also the slowest of the two, involves the breaking of the bond between R and X. So the bond between R and X breaks down in the first step, which of course is a slow step. Now this bond between R and X is a polar bond. This X, as you know, in alkyl halide is a halogen, and you already know that there is a difference of electronegativity between carbon and halogen, halogen having the higher electronegativity, so that is why this bond is polar. And when it will break heterolytically, shifting these two electrons towards the halogen, which will be removed as a halide anion, and leaving this R group with a positive charge. So the first step involves the breaking of the bond between R and X, which results in the formation of a carbocation. So carbocation intermediate is produced in the first step. Now the second step, which of course is the fastest of the two, will involve the bond formation between the carbocation that was produced in the first step and the nucleophile that is used in this reaction. So the nucleophile, which here is a negatively charged species, will attack the positive carbocation, forming a bond with the R group. So these are the two steps involved in unimolecular nucleophilic substitution reaction. Now let's see what is the rate of the reaction, or what are the factors that affect the rate of reaction. So again, we have the general mechanism here, and as you know that this reaction completes in two steps. The first one is a slow step, the second is a faster step. The rate of reaction is actually determined from the slowest step. And so this slow step here, or the step 1, is the rate determining step because it is the slowest of the all. Now you can see here that the slowest step involves only one molecule, that is the alkyl halide. It means that the rate of reaction, which is dependent upon the slowest step, or it is the rate determining step, it involves only one molecule, so the rate will be affected by the concentration of the alkyl halide only. So we can write it here in this form as rate is directly proportional to the concentration of alkyl halide. If we remove proportionality and convert it into an equation, we have to add a constant k here. So this is the rate constant, and the rate equation becomes rate is equal to k into concentration of alkyl halide. Now you can see here that nucleophile or the concentration of nucleophile has nothing to do with the rate of reaction. It's only the concentration of the alkyl halide that affects the rate of reaction directly. Let's see the energy diagram, the energy profile diagram for a unimolecular nucleophilic substitution reaction. So we draw a graph which has reaction coordinate on one axis and the potential energy on the other axis. So in the first step, we have the substrate only, that is the alkyl halide. And as you saw in the previous slide, that in the first step or the slowest step, the bond between R and X breaks. But before breaking, it will go through a high energy transition state. So you can see here we have a substrate that is of lower energy, but as the bond starts to break, these R and X groups, they move apart from each other, and you can see a delta positive and a delta negative charge created on R and X, and this high energy state is the transition state. And if you remember, in the first step there is formation of a carbocation intermediate. So as soon as this bond breaks, energy will go down and we will have the formation of the carbocation intermediate. Remember that intermediates are always of lower energy than their corresponding transition states. Here we have the completion of the first step, because the bond between R and X has been completely broken and we have the formation of a carbocation. Now in the second step, this carbocation then reacts with the nucleophile. So before formation, again, this bond will go through a transition state, a high energy state, and then finally energy will drop down to form the products. So when this intermediate starts forming a bond with the nucleophile, another transition state, the second transition state, is produced, and then these two groups, they come close together into the bonding distance and form a complete bond. These products now have lower energy as compared to all the transition states, intermediates, and even the substrate. So this is how the energy profile diagram of a unimolecular substitution reaction looks like. You can see here that the two transition states are also of different energy. The first one is of higher energy and the second is of lower energy. Why is this so? Because in the first transition state, we are going from a neutral molecule to form a high energy intermediate. You know that the charged species, whether they're positively charged or negatively charged or even radicals, they are of higher energy than the neutral molecules. So in the first step, we are going from a neutral molecule to a high energy intermediate, and it goes through a transition state which has to go through, or it has to cross a high energy hill, and to do so it needs energy. This substrate needs some energy to cross this energy hill, and this energy is known as the energy of activation or activation energy. Now this second transition state is of lower energy as compared to the first transition state. Why? Because in this case we are going from a high energy intermediate to a low energy stable product. So it's a feasible process and it will require less amount of energy to cross this hill and convert into products. Now let's see if any stereochemistry is involved in SN1 reactions. So we will explain this with the help of an example. We have this 2-bromobutane here which reacts with water in the presence of ethanol, and you can see from the products that this bromide group is replaced by OH from water. So we have the formation of a secondary alcohol, but we have more than one products. We have in fact two products, and we will see in a while that both the products have different stereochemistries. Why is this so? So this secondary alkyl halide or bromobutane goes through SN1 reaction, and as you know that it goes through it completes in two steps. The first step is the bond breaking between the R group, which in this case is a butyl group, and the halogen. So when the bond between the halogen and the R group breaks, we have the formation of a carbocation. And as you know that that the carbon which bears a positive charge, a carbocation, is sp2 hybridized, and the geometry around an sp2 carbon, of course, is trigonal planar. So we have the formation of a planar carbocation in which all the three groups attached to this central carbon will all be in the same plane. And this planar carbocation presents both of its faces for attack by the nucleophile. So you would think that there is an equal opportunity for the nucleophile to attack from this side or from this side of the carbocation, because this carbon here has an empty p orbital now, and it has lobes above and below the plane of these three groups. So both the lobes are available for attack by the nucleophile. We will see in a while if both the faces are equally available or otherwise. So let's see the stereochemistry. We are starting with a substrate with a reactant that has R stereochemistry, or absolute configuration is R. I hope you know how to determine the absolute configuration of molecules, or the R and S configuration of molecules, but still, if you want to learn it, you can find a link here which will guide you through how to determine the R and S configuration of stereocenters. Now this R molecule is converted into these two alcohols. The first one has absolute configuration similar to the substrate, that is R, and the second one has an opposite stereochemistry, that is S. And this proves that both the faces of this carbocation, which is formed after breaking of this carbon-bromine bond, are available for attack. So if the OH group attacks from this end, we will have the formation of one stereoisomer, and if it attacks from this face, we will have the formation of the other isomer. So we are starting from a stereochemically pure isomer, and we are ending up with two alcohols having similar groups but different stereochemistry. So do you think we have the formation of a racemic mixture? Because if R and S are in equal concentration or proportion, then we will have a racemic mixture and an optically inactive molecule. And you can see here that the planar carbocation presents both of its faces for attack by the nucleophile. So we can expect the formation of a racemic mixture. But that is not the case. Why? It is because of the fact that when the bond between carbon and bromine breaks, this bromide ion, which is formed as a result, still exists closer to this carbocation as an intimate ion pair. Because this carbocation is positively charged, so bromide ion that is released will try to be closer to this carbocation. Now what it does is that it blocks one of the sides temporarily. This side is blocked for attack, not completely but temporarily, and this other side of the other face of the carbocation is open for attack, or predominantly the nucleophile attacks from this side. So it means that one of these isomers will be formed in higher percentage than the other. Remember that this side is not blocked completely or permanently, but it's a temporary blockage, but still the percentage of the isomer forming by attack from this end will be in higher percentage than the one attacking from this side. So the overall stereochemistry of SN1 reaction is inversion of configuration. We may expect racemization, but racemization does not occur. In fact, we have inversion of configuration. So of the two isomers that are formed here, S will be formed in higher percentage than the R isomer. Now let's see what are the factors that affect the rate of reaction of SN1 reaction mechanism. The first factor that affects the rate of reaction is the substrate itself. Now the substrate, which is alkyl halide in this case, can be of different types. We can have a tertiary alkyl halide, we can have a secondary alkyl halide, or we can have a primary alkyl halide. And I have written all of them in an order. And you can see that we have a greater than sign towards the tertiary alkyl halide. That means that the rate of reaction in SN1 will be greater for the tertiary alkyl halide, which will be greater than secondary, and which will be greater than primary alkyl halide. Why is this so? It is because of the fact that when we have a tertiary alkyl halide and the bond between carbon and X breaks in the first step, we have the formation of a tertiary carbocation, which is more stable than a secondary carbocation that is generated from a secondary alkyl halide, and which is more stable than a primary carbocation that is produced from primary alkyl halide. So molecules which have the ability to form tertiary carbocations will fancy going through SN1 mechanisms. Primary carbocations will not favor SN1 mechanism. Secondary carbocation may or may not go through SN1 mechanism. The second factor that affects the rate of reaction is a solvent. If we have a polar protic solvent having a high dielectric constant, it will stabilize the transition state. Which transition state? It will stabilize the first transition state. And when the first transition state is stabilized, you saw that the energy required for the reaction to be initiated is the activation energy, and that is the energy gap between the reactant and the first transition state. If that energy gap is lower, the reaction will proceed with a faster rate. But if that energy gap is higher, it will need a lot of energy to go through that energy hill, and the rate will be slower. So if we have a polar protic solvent, it will stabilize the first transition state, making the activation energy lower, requirement lower, and so the rate of reaction will be higher. And this is what I told you earlier, that the activation energy is lowered, and so we have a faster rate. Then we have the leaving group. The rate of reaction is also dependent upon the leaving group. Let's see how the leaving group affects the rate of reaction. So if we have a good leaving group is any group that is happy to leave the molecule in the form of a negative anion. So if we have a good leaving group, the rate will be faster. Now, in case of alkyl halide, we could have alkyl iodides, alkyl bromides, alkyl chlorides, and alkyl fluorides. And again, I have arranged them in decreasing order of rate of reaction, which means that the rate with iodide will be faster than bromide, chloride, and fluoride. So moving from iodide to fluoride, we are actually increasing the charge density. The reason why iodides react faster or have a faster rate of reaction is because of the fact that when the bond between carbon and iodine breaks and iodide anion is formed, it is slightly more stable as compared to all the other three anions, because it has a lower charge density or the lowest charge density. Its size is bigger and the charge on all of them is similar. So when we have a bigger size with a smaller charge, the charge density is lower, and that means it is relatively more stable. When you go to the extreme right, we have fluoride, which has the smallest size, and the charge of course is the same, so it will have the highest charge density and it will be the least stable. So a reaction that involves the formation of a relatively stable anion or cation will obviously be more feasible as compared to the one that has a relatively unstable anion formation. So charge density increases in this way, and that decreases the stability, and that is why the rate of reaction decreases when we go from alkyl iodides to alkyl fluorides. So this was all about nucleophilic substitution reactions that are unimolecular or SN1 reactions. We'll meet again with SN2 reactions. So stay tuned and wait for the upcoming videos. Thank you so much for watching.